Okay, now in lecture 13 we are going to prove few more concurrencies. Now let us just revise what was our AB1. AB1 was given P on AB, that is angle bisector, then to prove that P is equidistant from arms of that angle. That was our AB1, and AB2 was converse of this, that if the point is equidistant from the arms, then it lies on angle bisector. Now consider triangle ABC, its exterior angles. AB is extended up to L, AC is up to M, so we have got exterior angle of triangle ABC, CBL and BCM. So we are considering two exterior angles of triangle ABC opposite to A, and we find that if we draw bisectors of these two exterior angles, then let this bisector be U, let this bisector be V, then let them intersect at point P. Then we are supposed to prove that the third angle bisector, which is internal angle bisector of angle A, is also going to pass through P. This is concurrency of two external angle bisectors and one internal angle bisector of triangle ABC. So pause this video, check whether you can do it yourself or not. It is similar to internal angle bisectors concurrency, two external, one internal. After the pause, we will give you the solution. Okay, now because P lies on U, we have PD1 is equal to PF1 by AB1. As point P, which is point of intersection of two external angle bisectors, is on bisector U, it is equidistant from the arms. Therefore, PD1 is equal to PF1. Now P lies on V also. Therefore, PD1 is also equal to PE1 by AB1. And now, if we look at these two equations, we get PF1 is equal to PE1. So if a point is equidistant from arm AB and arm AC, that is what we got here, then by AB2 P lies on angle bisector of angle A. This is how we get the proof. So this angle bisector, if we draw, then it will pass through this point, and all the three bisectors, two external and one internal, these bisectors will be concurrent at P. Now this point P is known as excenter and denoted by I1, excenter. If you observe I1, it is equidistant from arm AB, arm AC and side BC. Therefore I1F1, I1D1 and I1E1, they are equal. Something similar to in radius. This is called X radius and denoted by R1. R1 X radius. Okay, and now if we take I1 as a center and try to draw a circle with radius R1, we will get a circle touching again sides AB, BC and CA, the of three sides of the triangle, and this circle is called excircle. Okay, because of one concurrency we got excircle. So how will we write excircle? Circle with center I1 and radius R1. Now what okay, it is given a little later, but let me tell you right away that whatever work we have done opposite to angle A, similar work can be done opposite to angle B and opposite to angle C. So if there exists one excircle, that means there exists three excircles. If there exists one excenter, that means there exist two more excenters, and obviously they are denoted by I2 and I3. I2 is opposite to B, I3 is opposite to C. Their corresponding exradii will be expressed in terms of R2 and R3, and again those circles also will be called excircles. So 3 excircles and 1 incircle are the 3 circles which touch line AB, line BC and line CA of triangle ABC along with incircle. So total 4 circles, incircle and 3 excircles. So hope this configuration is clear to you. Now the way after doing in radius configuration, we have got now excircle configuration. Let us calculate perimeter once again. Okay, but before that let us use the property that we have proved in earlier lecture, that if F1 ID1 they are congruent, BI1 is angle bisector of B, this is 90 degree, these two angles are equal, so we get a property which we are calling as distance of a foot of perpendicular from vertex DFAV. It is in earlier lecture, that notation. So by that same proof, by RHS or SAA, we can prove these two triangles congruent, and hence we will get BD1 is equal to BF1. It is if we draw tangent to a circle from the point outside the circle, the lengths of the tangent, that means the point and where those tangents touch the circle, these two distances are always equal. That is what is this. So BD1 is equal to BF1. Again, C is the point which is outside this circle. Therefore, CE1 is equal to CD1. And A is the point which is outside this circle. Therefore, we get AF1 is equal to AE1. So these distances are equal because of circle, excircle opposite to A. Now, if these three quantities are equal, let us calculate perimeter once again. Perimeter is equal to AB plus BC plus CA, which is AB plus BD1 plus B1C plus CA. By the way, this D1 notation is foot of perpendicular from I1 on BC. E1 is foot of perpendicular from I1 on CA. And F1 is foot of perpendicular from I1 on AB. So I am breaking this BC in two parts, and then just now we have proved BD1 is equal to BF1. So AB plus BF1 is equal to CD1 is equal to CE1 plus E1C plus CA. Now if you look at AB plus BF1 in the diagram, you get it is AF1. And if you look at E1C and C1CA, it is AE1, which is 2 times semi-perimeter. And this identity says the both of them are equal. Therefore, AF1 2 times AF1 is equal to 2 times AE1, which gives us distance AF1 is equal to distance AE1 is equal to semi-perimeter. So the fourth term in the Heron's formula, which was there apart from S minus A, S minus B and S minus C, was S, and now we got that distance S in the triangle geometrically available between the vertex and excircle touching the side opposite excircle touching the sides of that triangle A. This distance is equal to S. Okay, so now if I look at distance AF1, which is S, out of which AB is small c, therefore I will get BF1 is equal to S minus C. BF1 is S minus C. But BF1 is equal to BD1, therefore this is also equal to S minus C. if I look at AC, AE1 is also S, therefore AC is small b, therefore CE1 is equal to S minus B, but CE1 happens to be equal to CD1, therefore that is also equal to S minus B. So in this configuration, S minus B is available at two places, S minus C is available at two places, S is available at two places, and this is happening again. 6 segments in this configuration are somewhere related to the terms available in Heron's formulae, and this is happening in front of A. Exactly similar things will happen in opposite to B and opposite to C. So we have many different lanes which are available over here. If it is opposite of A, then I have S minus C and S minus B. S minus A is missing. If it is opposite of B, the lanes will be S minus A, S minus C and small s, S minus B will be missing. And if we do the same work opposite to C, then we have S minus A, S minus B and small s, S minus C will be missing. After this we will create a table, we will try to draw that diagram and explain you all the distances. Once we are done with those 6 into 4, 24 distances, it is important that you try to remember all those distances. They are very, very required eventually, and spontaneously you should be able to say this is the distance S minus A or S minus B or S minus whatever. So I hope up to this point you have understood. And in circle, in center, the moment we got in center, we have got one formula for finding out area of triangle. Now we have got excenter opposite to A. Let us see if we can get one more formula for finding out area of triangle. Now, one thing before we go there, if I want to find out area of ABC, obtuse angle triangle, then by using half base into height, then if I use AB base, then what will be my height? The height will be drop perpendicular from C onto line AB. Whatever is that distance is your perpendicular. If I want to measure the area of triangle ABC with BC as a base, what will we do? Drop perpendicular from vertex, third vertex onto line BC. This will be your perpendicular. And if I want to find out area of ABC using AC as base, then drop perpendicular. So if the triangle is obtuse angle triangle, the only one put up perpendicular is within the side, the obtuse angle. From obtuse angle, if you put up perpendicular, that is the only perpendicular which is between A and C. And if you drop perpendicular from the remaining two vertices on the opposite side, then they are outside that side. So we will keep this in mind and try to figure out what would be the area using of triangle ABC using excenter I1 ABC. Okay, now we have drawn all the three angle bisectors. Let me draw the put up perpendiculars D1, F1, E1. Okay, so now triangle ABC is equal to, I want to write down area of triangle ABC in terms of triangle I1 AB, I1 AC and I1 BC. Pause this video, find out what signs should I put here in between, so that if I do that algebra, I will get area of triangle ABC. It is a very interesting exercise. It is just looking at the diagram and adding and subtracting or whatever, doing some algebraic operation with the areas and finding it out. Okay, so if we look at the figure, it will be add these two areas and subtract this, we will get area of triangle ABC. Now area of I1 AB is equal to, AB is a base, AB is a base which is small c, and IF1, this is small c, this is small b, this is small a, IF F1 R1 R1 R1. So CR1 upon 2 plus I1 AC is BR1 upon 2 minus I1 BC, which is AR1 upon 2. So now we get R1 inside bracket C plus B minus A upon 2. And in earlier lecture, last lecture, when we proved Heron's formula, we have said that this identity is R1 into S minus A. So we have yet another formula for finding out area of triangle ABC, which is using R1, which is radius of X circle opposite to angle A, which is R1 into S minus A. If we do similar work opposite to B, we should get formula for finding out area R2 into S minus B. And if we do similar work opposite to angle C, we should get formula for finding out area of triangle R3 into S minus C. Now, you have to try yourself whether you find out these two formulae independently or not. You have to figure out what happens if I draw X circle opposite to B, which distances I can get. So, in this lecture, we have covered one sample opposite to A. What happens opposite to A? And we have found out many different things in this lecture. What you need to do is similar things happening opposite to B and opposite to C. What are the distances available and what will be the total picture? We will eventually draw that. But before we end this lecture, we have one more thing to do, and that is basically if I extend this and draw external angle bisector of angle AC, say K, external angle K, then I am supposed to prove that CI1 and CI2 eventually they are opposite rays and they are collinear. So pause this video, check whether you can prove that the bisectors of angle BCM and angle ACK, that is CI1 and CI2, they are opposite rays and hence I1, C and I2 they are collinear. It is denoted by I1 dash C dash I2. They are collinear. Pause this video, check if you can prove that they are collinear or not. Another thing which is, we already know that if this is internal angle bisector, then another thing that need to be proved, this is I. So CI and CI1, CI, ray CI and ray CI1, these two rays, they are supposed to be perpendicular to each other. CI and CI1 perpendicular. So this is already done in earlier lectures. In some other context, check whether you can do it independently. CI is internal angle bisector of angle C. CI1 is external angle bisector of angle C, which is BCM. They are supposed to be perpendicular. Similarly, CI and CI2 also we can show perpendicular. So if you do this thing, you will get this thing easily. Or you do this thing first, you get that thing. And I want you to eventually think that I1C, I2, I2A, I3, I3B and I1, they form a triangle I1, I2, I3. So eventually we will have a triangle I1, I2 and I3. And if we observe that I3C is perpendicular to I1, I2, I1A is perpendicular to I2, I3, and you will find that I2B is perpendicular to I1, I3. So these three are perpendicular. So I am just drawing. If we do everything outside B and C, then the triangle would look like this. And the AI1, which was angle bisector of triangle ABC, AI1, which was angle bisector of triangle ABC, happens to be, if we look at it as I1A happens to be altitude of triangle I1, I2, I3. Similarly, BI2 was angle bisector of angle B of triangle ABC, happens to be I2B, which is foot of perpendicular, so altitude. So the major result here is the angle bisectors are concurrent at I. Angle bisectors of ABC are concurrent at I, and if I look at triangle I1, I2, I3, the lines are same, the point is same, but then they are altitudes which are concurrent at the same point R. So I is in center of triangle ABC and I is orthocenter of triangle I1, I2, I3. Okay, so now apart from the homework that you have in this lecture, only 4 problems, few of them are numerical, but then you are supposed to take a big drawing paper and draw all these things at actual. We call that figure as mega figure. What you do is take a scaling triangle, not isosceles, not equilateral, no special triangle, bisect the angle, internal angle bisectors, draw external angle bisectors, draw perpendiculars from I1, I2, I3, get these points A, B, C, D, D, E, F, D1, E1, F1, D2, E2, F2, D3, E3, F3, draw small incircle, excircles as far as possible, create a big diagram, and then we will discuss that diagram maybe in the next lecture and find out what all distances that we have found out now, how to remember them. Hope we have done a lot of work in this particular lecture number 13. Go through the notes, draw your own pictures, try to understand everything, try to digest, try to remember. Once you understand everything, it will be there for you forever. Okay, thank you.